Hi, I'm Alex from EDD Academy, and today we're going to be talking about implicit differentiation. So, you may ask, what is implicit differentiation and why do we need it? So, before I get into that, I'll explain what the opposite of it is, which is explicit differentiation. So far we've looked at equations and taken the derivatives of equations with the form y equals f of x. As you can see here, y is explicitly defined, hence the equal sign, in terms of x. On one side there's y, on one side there's x. But that's not the only type of problem we can look at with derivatives. We can consider the tangent line, or the derivative, to another type of problem. Let's say where y is being manipulated as well, the left side is also being manipulated. An example of this is the equation for a circle, which is x squared plus y squared equals r squared, or y squared equals x. This is a circle with radius r. I'll center it at the origin. And this graph looks like this. So how do we actually compute the derivative of this? Instead of rearranging and defining y explicitly in terms of x, which we could do in those problems, just leave it as is. Let's take the example y squared equals x, for example. As I said, we keep both sides of the equation the same and just go ahead and differentiate. We take the derivative of both sides. So ddx of y squared equals ddx of x. Computing the derivative on both sides, this is the important step. So we take the derivative of y squared, which is 2y, but instead of just leaving this here, we have the chain rule we learned last time, and any y term you have to multiply by f prime, y prime, or dy dx. So I'll do that here. For any term involving x, you just take the derivative of that without the chain rule as normal, and the derivative of x is just 1. And then our final step is isolating this dy dx factor. So we can divide both sides by 2y, and we get that dy dx equals 1 over 2y. This is our derivative. In general, there are a couple steps to this process. Like I said, you differentiate both sides. With respect to x. Step 2, you make sure any derivative of y terms has a factor of dy dx. And finally, you solve or isolate the dy dx term. I'll pause a second so you can look at the screen. Okay, so now we can look at our first example. It says that find dy dx if x squared plus y squared equals 25. Note, this is very similar to the equation of a circle that we saw a couple slides ago. So computing this derivative, like we said, we can go about that by differentiating both sides. So we have that ddx of x squared plus y squared equals ddx of 25. Note that in this problem, both the y terms and the x terms are on the same side of the equation, but that doesn't change any of our differentiation rules. So we can see that this is a sum rule, so we can rewrite this as ddx of x squared plus ddx of y squared equals d dx of 25, but 25 is just a constant, and the derivative of constant is 0, so this side is equal to 0. Actually computing our derivatives, the derivative of x squared is simply 2x, and the derivative of y squared is 2y. But note that y is a function of x in this case, because we are differentiating with respect to x, so that means we need to use the chain rule and slap on that extra dy dx factor, and that still equals 0. And then remember that our last step was to solve for dy dx, so we can do that here. 2y times dy dx equals 0 minus 2x. We subtract 2x from both sides. Then we have that 2y dy dx equals negative 2x, and we can divide both sides by 2y, giving us that dy dx equals negative 2x over 2y. The 2's cancel, so dy dx equals negative x over y, and that is our derivative. Moving on to our second example, we notice that it's slightly more complex than the first in that it has both x and y terms on both sides of the equal signs, but nonetheless, our differentiation rules remain the same, and we can go about differentiating implicitly in the exact same way. And the first step of doing so is taking the derivative of both sides. So immediately we can see that there's a sum rule on both sides, so we can write d dx of x squared y cubed plus d dx of 6x squared, covering those terms on the left side, equals d dx of y plus d dx of 12. We can simplify this, noting that this here is a product rule, so we can write that x squared times the derivative of y cubed plus y cubed times the derivative of x squared. That takes care of the product rule, this first term on the left here. And then we add this to the derivative of 6x squared, which is just 12x, and that takes care of the left-hand side here. And this entire thing equals the derivative of y is just 1, but because it's a y term, we have that dy dx term slapped onto it. So dy dx plus the derivative of 12, but 12 is just a constant, so its derivative is 0. If we take the derivatives of the rest of the terms in the product rule, we have that x squared times, so the derivative of y cubed is 3y squared, and we have that extra dy dx term at the end, so 3y squared times dy dx plus y cubed times the derivative of x squared. The derivative of x squared is just 2x, so we have plus 2x y cubed plus 12x equals dy dx. We can manipulate this a little bit, factor out a term of 3x squared y squared minus 1. That minus 1 term comes from subtracting the dy dx onto this side to isolate it, try to get it on the same side. And we can also subtract some other terms, and we get that 3x squared y squared minus 1 times dy dx equals negative 2x y cubed minus 12x. And because we want to isolate this dy dx term, we can divide both sides by this factor term right here, and we get that our derivative, dy dx, equals 2x y cubed plus 12x over 1 minus 3x squared y squared. Note we got rid of this negative here by canceling it with this negative here, and this is our derivative. This is our final example in the implicit differentiation video. So if we take a look at this example, it reads, find dy dx if sine of x plus y equals y squared cosine x. I included this example because it reiterates that we always need to keep in mind trig knowledge, and I just wanted to combine both derivatives of trig functions with implicit differentiation. It doesn't change the problem at all, that was just something I wanted to know. So if we go about differentiating implicitly, we have to take the derivative of both sides. So we see this left-hand term on the left side. This is a demonstration of the chain rule. So we have that in this case, the outer function is sine, and we leave the inner function the same. So the derivative of sine is cosine. So we have cosine of x plus y. And with the chain rule, we have to multiply by the derivative of the inside. And the derivative of the inside is, so the derivative of x is just 1, and the derivative of y is just 1, but because it's a y term, we need that dy dx or y prime term. In this example, I'm going to be using y prime instead of dy dx because I used dy dx in previous problems, and I just wanted to make sure our viewers have exposure with both. So 1 plus y prime. And then on the right side, we have a product rule example. So we have that y squared times the derivative of cosine x, and instead of writing it out like I have in the past problems, I want to emphasize that these derivatives, the more we do, the faster they should come to you, and the more we should be doing them in our heads. So the derivative of cosine x is negative sine x, so we can just write that here. And then because we're using the product rule, we add cosine x times the derivative of y squared, which is 2y, and then slap on that y prime term. So we have cosine x times 2y, y prime. If we simplify this, we have that cosine of x plus y. We can rearrange some of these terms because we want to isolate our y prime term. So we can write cosine of x plus y plus, bring this from the other side, bring this term, so plus y squared sine x. And yeah, now that we've brought our y primes all to one side, the right side reads 2y cosine x y prime, as you can see from our terms here, and then minus cosine of x plus y times y prime. Note we just distributed this factor here. So dividing on both sides, we have that y prime equals y squared sine x plus cosine of x plus y divided by 2y cosine x minus cosine of x plus y. This looks a bit complicated, but that's our derivative. Thank you for watching.